Good morning, everybody. Today, for Math 133, we are going to be talking about the Chapter 9 project. It's day 20. Uh, yeah, so Chapter 9, 10, and 11 projects, they're not in Google Sheets. They are actually in your course pack. And so you're going to want to go to page 569. Page 569, 569, that has the Chapter 9 project. It is 5 pages, so make sure you grab all 5 pages. Usually our uh, worksheets are like 4 pages, but this one's five. So. Um, don't forget to do the 9.4 lecture notes. There's also some lecture notes for the flow chart for Chapter 9. And you're allowed to use those flow charts on test day. So you want to definitely make sure that you have those. Um, and okay, so page 569, you're also going to want to make sure that you've got your data that we collected on Tuesday for your M&Ms and your Skittles. Okay. Um, it's okay if they're already eaten. We've started eating ours. Uh, I just need the numbers. Okay. So whatever it was before they got eaten, right? So you'll want to make sure you pull that up because we're going to need that to fill out the project. Okay. Um, yeah. And then if you attend one of the Zoom sessions this week, you do not need to fill out the discussion board. If you are listening to this on the recording and you missed both the Tuesday and the Thursday Zoom session, make sure you go and fill out the week 10 discussion board. Okay. If you have attended the Zooms, it might say like, "Hey, you need to go fill this out." No, just like all of our other discussion boards, as long as you know that you attended one, you'll get your points. Okay. I just have to go in there and award those. Okay. Um, all right. So page 569, 569. Um, Candy with confidence. We're going to be making confidence intervals for the data that we collected around our candy. Okay. Answer the questions in the box and then scan and upload. You need 4 decimal places. All right. Um, so for this project, we are going to be doing we're going to be building some confidence intervals, and so we need some confidence levels. Now, uh, we're going to get 3 confidence levels here, um, and it's asking us to do them randomly. Select 3 random confidence intervals. Okay. Now, I want to point out that in practice, that's not what you do. You don't just say like, "Yeah, just give me a random number and we'll use that." Okay. Um, when you are building a confidence interval, like if I was building this for my boss or my team leader or the CEO of the company or whatever, um, I'd want to start with asking them how um, how confident do we need to be in these numbers? Okay, we can never be 100%. Okay, to be 100% confident means we would need to sample the entire population. And we've already established that we can't do that. Okay. So if I wanted to know what proportion of M&Ms are red, what proportion of M&Ms are red, okay? I can't actually calculate that because I would need to open every single bag of M&Ms in the world and count them. And you can't do that. Okay. So we took a sample on Tuesday. The bags that you bought, um, the M&Ms you bought, those were our samples. Okay. And we're going to use those samples to make a approximation for the proportion of M&Ms that are red or green or whatever color you want. Okay. So um, is our approximation is our proportion that we're going to calculate today going to be perfectly accurate? No, it's not because we did a random sample And so you might randomly get a couple more reds or a couple less reds. Okay. So it's not going to be exactly the same as the population proportion, but it's going to be really close. Okay. How close? That's what a confidence interval is. It's telling you how close your sample's estimate is to the actual population proportion. Okay. Now, we can do do the same if we were looking at means, like if I was, measuring like average height of people or people's average age or something like that, we could do the same confidence interval building for means, okay? But for M&Ms, for all of the projects that we're going to be doing for the rest of the semester, we're going to be focused on proportions, okay? All right. Anyway, let's jump into this. Um, so instead of actually having a conversation with my boss and asking like how confident do we need to be in these numbers, we're just going to pick random confidence levels. So there's a random confidence level link in Canvas. I will drop it in the chat for you. So if you click on the Chapter 9 project, random confidence level, if you click on that, it's going to give you this, and I'm going to drop this in the chat right here. Make sure you sign in or register. So there we go. Okay. So these are confidence levels. A confidence level, we want to be super confident, right? We want to be very confident in our answers. So these numbers go from 70% up to like 99.8. Okay. Even that, like you could get even more accurate. You'll remember that three standard deviations is 99.97, or sorry, 99.7. So I guess this is a little more than three. But yeah, 100% is not on here, okay? Because if you wanted to do 100%, you would have to sample the entire population. But 99.8, that seems real confident, okay? Um, okay, so a good confidence interval, remember that we defined something as an unusual event if the probability was less than 5%. So 95% is the normal confidence level that you're going to see people use all the time. Okay. Um, Now you don't have to use 95, and here today we're going to use one of these numbers, and it doesn't have to be 95, but 95 is what people will usually use if they're not sure what confidence level to pick. Okay. So anyway, but that's not what we're going to do. We are going to select three confidence levels, three random confidence intervals. And to do that, we're going to do data, sample, and then choose the confidence level column and a sample size of three and then click compute, and then we'll put our answers in here. Okay. So we're doing I don't know, this, let's see. So data, sample, select the confidence level, and then put a sample size of three. Okay. Um, so this is not the sample size for our M&Ms or the sample size for our project. Basically, all we're doing here is I want StatCrunch to select three of these numbers at random. Okay. That's what's happening here. So I did uh, data, sample, selected confidence levels, sample size of three, hit compute, and it's going to give you three of those numbers at random. Okay. So you're going to write those on these three spots here. Okay. And your numbers will be different from mine because it was selected randomly. So I randomly got 87.3% and 98.3% and 94.8%. Okay. Those are the ones that I got. You're going to get different ones. Okay. Oh, there's my desktop. All right. So, all right. So now that I have those, um, let's start with looking at M&Ms. We're going to use the confidence level number one. This one's going to be for M&Ms. Okay. And then this one is going to be for, um, this one's going to be for Skittles, right? And then this one is going to be for sample size calculations. Okay. Yep, I can show you how I did that in StatCrunch again. Okay, so once again, what I did was I clicked on in Canvas, I clicked the Chapter 9 project. There's a link here for the random confidence level file, which will pull that up in StatCrunch. You're going to go to Data, Sample. You're going to select confidence levels, and you're going to put in a sample size of 3, and you're going to hit Compute, and it's going to give you 3 random numbers. And you'll notice I got different random numbers this time, right? 78, 97, and 99.8. That's the biggest one. Well, biggest one from here. Obviously, you could go bigger if you wanted. So, okay. Um, all right. Once you've got those 3 and wrote them down, we're going to start with our M&Ms, okay? Question number 2. Which M&M color had the lowest count in your sample? If there's a tie, just pick one of those colors, okay? Fill out this table for that color. So that's why I need my data. So for my M&Ms, I had blue was my lowest. I had 21 blue. Okay. So X is how many blues you had. N, you'll remember that we use the symbol N for sample size. Okay. So how big was my sample? I collected 140 M&Ms. That's how many I bought. So that is my sample size. Okay. P hat. So that is not in the table in the data that we collected on Tuesday. I have to calculate that. So um, you'll remember that probability is the number of wanted outcomes divided by the total. So I want to look at what's the probability of blue in my sample. So I want the blue, that's my X, that's going to be in the numerator. Out of my total sample size is N. P hat is equal to X over N. So we'll need to put that in the calculator. So I had 21 divided by 1. So my proportion is 0.15. Oh, it's nice and round. 0.15. Now, if you had more decimal places, like give 3 decimal places for p hat. Okay, so I guess I'll give 3. My is 0.150. Okay, right. So if I had, if my sample size had been, or sorry, if my blues had been 120, I would have put it as 0.14143. Right. Right. Anyway, I got a nice round sample size. That never happens. Um, okay. Uh, so, uh, that's my that's my probability for blue. So, um, verify whether all the requirements for constructing a confidence interval for the proportion of this color of M&Ms are satisfied. Okay. So we need to do random, independent, and norm. Okay. So in order to construct an accurate confidence interval, I need to satisfy the central limit theorem for proportions. Okay. Uh, so it says construct a confidence interval. It doesn't say anything about central limit theorem, but the central limit theorem is what allows us to build confidence intervals. It's what allows us to do hypothesis testing in chapter 10. So we're going to be checking random and independent and normal throughout the rest of the semester. Okay. So Caleb's got a question. Was X the lowest number? So yeah, in my M&Ms, you're gonna find whichever one is the lowest. My lowest number was 21, and it was for blue. Okay. So if yours was a different color, that's totally fine. Okay. So you're just gonna write that number. Now, is X always the lowest number? No, 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 no. X, you'll remember X is the event that you're looking at. And in this case, they told us to go find the M&M that had the lowest count. Okay. So if we wanted to look at highest count, my X would be whatever my highest number is. Or if they said just how many blues did, or sorry, let's say how many greens did you have? I would just write X's, however many greens. So X isn't necessarily the lowest, it's lowest because that's what they told us. Okay. So for other chapter nine, when we look at chapter nine review, X is the event that we are building the confidence interval around. So all right. Now that we've okay, so question number three, verify whether the central limit theorem, verify whether the requirements for constructing confidence interval are satisfied. So first of all, random. So did we select a random sample? Well, did anyone go was did anyone go to like one of the M&M stores where they have maybe like the big bin of M&Ms and pick out like all the blues? No, nobody did that, right? You went to like Meyer and you bought a bag that was already sealed. So you selected just a random bag, right? So um this is a yes because every candy, every M&M had equal chance of being in your bag. So, in order for a sample to be random, every element of the population, every person, or in this case M&Ms, every M&M has to have equal chance of getting selected. And as far as I know, none of you guys went to the M&M factory and were like, "I want all of these M&Ms," right? You just picked you just picked a bag and got what you got, right? So, so we're good there. Uh, independent. So for independent, I need to check that 20n is less than capital N. So for me, my n was 140. So I need to do 20 times 140. I get 2800. All right. And I need to check that that is less than all M&Ms. All M&Ms in the world. So let me ask this. Uh, are there more than 28,000 M&Ms in the world? Yeah, there's way more, right? So this is yes. This is for sure yes. Okay. All right. Normal's the one where things might fall apart. Let's see. For normal, I need to check n times p times q. That has to be bigger than 10. So independent, my sample size, it has to be, can't, is not allowed to be too big. Normal, my sample size is not allowed to be too small. Okay. And we're doing NPQ is bigger than 10 because we're looking at proportions, right? If we were looking at means, I would be looking at N has to be bigger than 30. Like if I wanted to know what the average weight of an M&M is, and then I would take all the M&Ms I had, I'd weigh each of them, and then I'd average those, and then we'd be looking at means. Okay. In this case, I'm looking at colors, and color is a qualitative variable. So we are looking at proportions. Okay. All right, so my N was 140. My P, I'm going to use p hat because I don't know p. Okay. P is is the symbol we use for the population. And we don't know the population proportion of blue M&Ms because I can't check everything. Now, when we're doing this project, we actually do know the answer. We do know what the P is, okay? But we're going to pretend that we don't, okay? Because that's what happens in the real world. In the real world, I don't know what proportion of people are going to vote for this person. I don't know what proportion of people have red hair. I don't know what proportion of people that this vaccine will work for, okay? Um, so Anyway, so for my P, I'm going to use P hat. If you want to write it as P hat, Q hat, you can, but you don't need to. A P in my case is 0.150, and I need my Q as well. So to get Q, I do 1 minus my P value, and I get 0.85. All right. So I need to multiply these three together, N times P times Q. See what I get. 140 times 0.5 times 0.85, and I get 17.85. Okay. Uh, is that bigger than 10? Yes, it is. So I am good. I got three yeses. Now, uh, I got three yeses. Maybe you did not. Uh, is there anybody here that did not get three yeses? Eva didn't get three yeses, and neither did Jadlyn. So, um, well, I said, did you get three yeses? So I'm gonna hope that you you didn't get it, that you got a yes on random, right? Because like I said, nobody went and picked out specific candies, right? You picked out just a random bag from, from the store, from Kroger. Uh, and I'm gonna also guess that you didn't get a no on independent because nobody went out and bought 5% of the world's M&Ms, right? So uh, you probably ended up getting a no on normal, and this is the one that people get no's on the most often. It's because our sample size might not be big enough, right? I had 140 M&Ms, and I was at 17. 17 is bigger than 10, but honestly, it's not that much bigger than 10. So uh, how many, so for those of you who got no's, how big was your sample size? So Montez had 208. Oh, but he got a yes. Okay. So Caleb. So Caleb only had 48 M&Ms. And so and that's fine, Caleb, by the way. Like you don't need to go and, and redo the project. You don't need to go buy more M&Ms or anything like that. Uh, I wanted to show that like when you have a smaller sample size, like 48 or Jadalyn had 106, that can cause problems. So 140 was fine. 106, it sounds like wasn't. Uh, um, for and then Eva had 104, right? And so they had smaller sample sizes. They probably also had much smaller p-values. My p-value was 0.15, which is actually pretty high for this project. Usually when I'm doing this, I have like p hat is like 0.1 or something. Uh, so how big was your p hat then, if if you had a no? Oh, Caleb only had a zero point 0.4. So you only had like four blues in your bag or something. Yeah. And then Jalen's was 0.10. So not only can having a sample size be too small be a problem, but if your p-value is too small, that can be a problem as well. Okay. So I'd mentioned the example of like commercials. So like here, a sample size of 140 for me was fine. Um, but if I was an advertising company and I wanted to see the effectiveness of my commercial, um, I'm going to need a huge sample size, okay? Because um, my p hat, my p value is the probability that someone will purchase my product after seeing my commercial. And a good p value for a commercial is like 0.5% or less, okay? People watch commercials all the time and see tons of commercials. We're bombarded with commercials, but we don't just go run out and buy every single thing we see on a commercial, right? So because of that, um, if I'm looking at a p-value of like 1%, so like, if I do a sample size of 140 people and my p-value is 1%, oh sorry, 1%, and my q value then would be 99%. That's only a value of 1.3. That is way lower than 10. So that is not a big enough sample size. Okay. Anyway, so if you find yourself in that situation where, oh man, I don't have a big enough sample size, um, we will talk about how to calculate what sample size you need on page 5. Okay. But for now, we're going to keep going. So if you have yes, 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 or if you have yes, yes, no, either way is fine. We're going to push forward to the next page, question number 4. Okay. All right. Question 4 says, regardless of whether or not the requirements were met. So if you got 3 yeses or if you didn't get 3 yeses, let's keep going. Either way is fine. Construct a confidence interval for the proportion of M&Ms that are your color from number 2. So mine was blue. Maybe yours is a different color using confidence level number 1. So we need to show the formula. We need to do the substitution. And then we need the result. Okay. All right. So, in other words, I want to know what proportion of M&Ms are blue. And I want to be 87% confident in my result. Okay. I'm going to use confidence level 1 for M&Ms. So what proportion of M&Ms are blue? Well, I calculated that with my sample, 15% of M&Ms are blue. Now, is that accurate? No, it's not, because I have a random sample, just a random bag that I bought, right? Um, but we can say that that is close to the actual population proportion. How close? That's what the confidence interval is going to show us. It's going to show us, well, the population proportion is somewhere in this range. 87% confident that it's somewhere in this range. Okay. Now so I had mentioned earlier, we actually do know the true value. The M&M company, they produce the same amount of each color. So there are 6 colors. So what is 1/6 as a decimal? 1/6 is 0.166. So 16.6%, 16.7% of M&Ms are blue. I say 15% of M&Ms are blue. Those are close, okay? They're not exactly the same because my sample was random, right? But they're close. And the bigger your sample size is, so the bigger uh your um bag of M&Ms was, the more accurate you'll be. I had someone on the call in the evening on Tuesday who they bought like a 2-pound bag. So they were still counting when the class was over. So yeah, but their estimate's going to be real accurate. So they're going to be real close to 1/6. Okay, so formula is going to be on page 259. Okay, so page 259, we have the confidence interval formula for a single proportion. single population, okay, for proportion. And then down here for a mean, okay? So uh, again, it's important to pay attention to whether you're looking at proportions or means. Technically, these are very similar, and so yeah. But anyway, we're going to be using this one. So our formula is this guy, p hat plus or minus z alpha over 2 square root p hat q hat over n. Okay, what a crazy formula. This formula looks pretty crazy. All this formula is doing is it's saying take your sample proportion that you calculated, which mine was 15%. Okay. 15% is what I think how many blues there are. There's 15% of blue M&Ms are of M&Ms are blue. Okay. And then you say, well, that's not that's not the actual number. The actual number is close to that. How close? Well, you add a little bit, you go a little bit above 15%, you go a little bit below 15%. How far should you go? That is the margin of error. So you go a little bit above, so you add your margin of error, and that gives you your upper value. You subtract your margin of error, you go a little bit below, and that'll give you your lower value. Okay. Margin of error is calculated as this, and this is just Z alpha times your standard, or yeah, times your standard error. Okay, we've talked about that before. We've talked about the formula for standard error. So anyway, all that said, here's our formula. That's what we're going to write. Question number 4. So you're going to write formula is p hat plus or minus. We're just going to copy this down. Z alpha over 2 square root p hat q hat. Okay, I'm just copying that formula. Substitution, we plug in all the numbers. Okay, so this is what that'll look like. So my p hat is 0.15. Okay, that's what I have on page 569. Okay, and your p hat will be different, so you plug in whatever that number is. Okay, I'll come back to z alpha over 2. So leave yourself a little bit of space. And then 0.150 is my p hat. Q hat is 0.850. And my n is 140. Okay. For z alpha over 2, I need to calculate that. So to do that, I'm going to do stat, proportion stats, one sample with summary. Okay. Or the other option is you can do what we did in chapter 7, which is you can do the stat calculator's normal. Okay. Either way is fine. I'll start with, so I'm going to go back over here to StatCrunch. I'm going to do stat calculator's normal first, just to show you what that looks like. Stat calculator's normal. Okay. And I want to find the z values when the red shaded area is my confidence level. Okay. So I'm going to switch to between. I'm going to put in my confidence level, which mine was 87.3%. Okay. So whatever confidence level you got randomly, the first one, that's what we're going to be using for M&Ms. So yours is going to be different from mine, okay? But that's fine, okay? Maybe you're at 95% confident, or maybe you're only at 70% confident, okay? Whatever is fine. So you're going to put in that number here, and you compute, and that gives you your z value. My z value is 1.526. Okay. So my formula, my numbers, so everyone's going to have the same formula, but you're going to have different numbers depending on how many M&Ms you had, how many blue or green or red or whatever the lowest one was. And then you're going to have a different confidence level. Okay. And so you'll put that in and you're going to get a different Z value. Okay. So again, what I did was I went to stat, calculators, normal. I switched it to between. Okay. And I'm doing between because between when you're doing a confidence level, it's always between because you're going from the lower limit to the upper limit. I want my population to be somewhere between this lower limit and this upper limit. Okay. I'm doing and then I put in my confidence level. In my case, it was 87.3. If you're at 95%, your Z values should be close to 2, right? So you're going to put in whatever confidence level number you had, put that in there. That's going to give you your Z value, and that's what you're going to put here, okay? All right. From here, okay, we are going to calculate our result. Now, at this point, there's two ways you can do it, okay? One is you can just type this into Desmos, okay? If you type this into Desmos, make sure you put parentheses under your square root. I think Desmos is smart enough that it can handle that. Normal calculators, though, you need parentheses there, okay? So you can type that into your calculator. That's one option. The other option is you can do what it says on page 259, stat, proportion stats, one sample with summary. Okay. And if you do either one you do, you're gonna get very small differences in your answer. Either one is fine. Okay. So I'll show you how to do it in the calculator first. So in the calculator, I'm doing my p-value and then do the minus one first. 1.526 times SQRT 0.150 times 0.850 divided by 140. And my lower limit is 0.104 decimal places 39. Okay. You just type that all in. Okay. You don't need to show work or anything. You just type it in. Now you type the minus. I did the minus first. If you just go back up here and change your minus to a plus, that will give you your upper limit, which in my case is 0.1961. And that's my upper and lower limit. Okay. Right. Now, that's one way to do it. Okay. I'm going to show you a different way to do it. Okay. If you don't want to type it in the calculator. And if you didn't want to use the stat calculator normal. Okay. So Stella's got a question. How do I do that in StatCrunch? I'm going to show you a different way right now that might be easier for you. Okay. So instead, I'm going to use this one, stat proportion stats, one sample with summary. So this is how that'll look. Close this out. Stat proportion stats, one sample with summary. Okay. This is going to calculate a confidence interval for you. Okay. Instead of having to put it in the calculator with the formula. So here's what you do. You put in your number of successes. So that would be your X value. Mine was 21. I had 21 blues. So whatever your X value is. Number of observations, that's your sample size. So whatever your N is. Mine was 140. We're going to be doing hypothesis testing in chapter 10, but I want to switch this dot over to the confidence interval one, because that's what we'll be doing in chapter 9. That's what we're doing on this project. Our level is the confidence level that we got randomly. Mine was 87.3%. Okay, so that's what I'm going to put in here. And then I'm going to hit compute. And this is going to give you a whole bunch of different things. Oh wait, it didn't give me my Z value. Uh, is there an option to get your Z value for this? Yeah,
Yeah.
there we go. Checkbox show the critical value. There it is. Okay. So all right, I'm gonna show you again. I do stat, proportion stats, one sample with summary, put in my X, put in my N, click this dot, put in my confidence level, and check this box to show your critical value. Okay. And then you hit compute, and there we go. Okay. So my critical value is right here, 1.526. That is the number I calculated in the calculator earlier. So you didn't have to do the calculator if you want to do this instead. If you want to do the stat proportion stats one sample with summary, it'll give it to you. Okay. And then my result is right here. My lower limit is 0.1039, and my upper limit is 0.1961. Oh, well, shoot. Mine are the same, which is good. That's fine. Um, yeah, but they're not always going to be the same. So, um, so I'll show you again what I did. I did stat, summary stats. Oh, no, not summary stats. Shoot. Stat proportion stats. Stat proportion stats, one sample with summary. I put in my X, how many blues I had. I put in my N, which is how many M&Ms total I had. Changed my dot over to the confidence interval. Put in whatever confidence interval number you have. Click the show critical value and then hit compute. Okay. And here's my Z value. Here's my lower limit. Here's my upper limit. Okay. Yeah, that doesn't really give me anything. I was curious if the plot gave me anything. It doesn't. Okay. So you're going to write your lower limit and your upper limit on your paper, and you'll put parentheses around it. Okay. So what this is saying is, I don't know what proportion of M&Ms are blue. Okay. I'm guessing it's close to 15%. How close? Well, I'm 87% confident that it's somewhere in this range. 87% because of that was the confidence level I'm using. 87% confident that it is somewhere in this range. It's somewhere between 10% and 19%. Okay. Now, if I wanted to be more confident, if I wanted to be 95% or 99%, then my confidence interval would have to change. Okay. Um, and also, if I used a bigger sample size, I would have been able to get more accurate. Okay. Because 10% to 19% is a pretty wide range. Okay. But anyway. Um, all right. Willy Wonka claims that the proportion of blue, portion of M&Ms of my chosen color, claims that the proportion of blue M&Ms is less than 1/6. Okay, so he thinks that there's something shady going on at the M&M company, and maybe blue dye is expensive, and they're not actually making as many blues as everything else. Okay, so does my confidence interval support his claim? Okay, so well, what is 1/6 as a decimal? 1/6 as a decimal was 0.1667, right? 0.166, 16%. Okay. He's claiming that proportion of blue M&Ms in the entire population is not this number. Okay, it's less than that. So I'm going to look at my confidence interval. Well, I'm 87% confident that the true proportion is somewhere in this range. okay? So all we need to do is we need to check, is this 0.166 somewhere in this range, okay? So imagine if you had, a number line here. This is the x-axis. My lower limit is 0.1039. My upper limit is 0.1961. Dead in the middle is 0.15, okay? Where does 0.16 land? So my confidence interval is this area here, this shaded area here, okay? 0.16 is like right here, 0.1667. So 0.1667 is in my confidence interval. So I think that he is not correct because 1/6 is inside my confidence interval. Okay. I don't know what the true proportion is, but I know it's somewhere in this range. And since it's somewhere inside of my range, then I think that his claim is incorrect. Now, for you guys, maybe your upper limit is not 19%. Maybe your upper limit is 13%. Then this 16% is not in the range, it's over here. If that happens, okay, then he's claiming that the true value is less than 1/6, and you don't know where in this range it is, but the entire range is less than that. If that's the case, you would be circling this one because the entire interval, all the shaded area, is below 1/6, okay, if that were to happen. So one of these is your answer, depending on whether 16% is in your range or not. Okay. So don't circle both. Okay. You'll circle one depending on what, your sample's telling you. Okay. Suppose that you had used a super giant bag with thousands of M&Ms in it, way more than what I had. But the proportion of your color was still the same. The confidence interval created during using the numbers from this big bag would have been what? Narrower, wider. So we're going to be talking about narrower and wider confidence intervals all through chapter 9. And uh, there is a table that is probably going to be really helpful that Elaine's provided that will, help you figure out which answer. I like to use this axiom that uh, a larger sample size means more accuracy, right? If you use a larger sample size, you are more accurate, okay? So if we look at that, a bigger sample size, so a bigger bag of M&Ms would have been a larger sample size, okay? And so that would have meant that you would have been more accurate. Your error would have been smaller. The error is the distance from the middle. This right here is your margin of error, and this right here is your margin of error, okay? So a larger sample size would have meant that your error would have been smaller, and so you would have had a narrower confidence interval because sample size and error have inverse relationships. So as your sample size goes up, your error goes down. That's what inverse means. So you'll circle one of these, but everybody should be circling the same answer for number 6. Okay. All right. That was our M&Ms. We're going to move on to Skittles. All right. Page 571, confidence intervals with Skittles. Which color had the highest count in your sample? Okay, we can do that. So for Skittles, mine was green. I had the most green, 54. X is the highest number in this case. So last time it was the lowest, now it's the highest because we're switching to, uh, it says find the highest count. My sample size is 238. That's my N. And P hat equals X over N. So I need to divide those. 54 divided by 238. And I get 0.227. Okay. So what percent of Skittles are green? I don't know, but I am estimating that it's 22.7%. That's my point estimate. That's close. It's not exact. There's some error there. We are going to calculate how big that error is, and we're going to add that and subtract that from our point estimate, our p hat, and that'll give us an upper range and a lower range, upper and lower value for our confidence interval. Okay. Verify whether all requirements for constructing confidence interval for the proportion of this color of Skittles are satisfied. So again, we need to check that it is random, independent, and normal. So random, yes, every Skittle had equal chance of ending up in my sample, right? For M&Ms, I don't think it matters. Like the colors, they all taste the same, right? So nobody's picking and choosing. But if you could pick and choose on Skittles, like I wouldn't pick any yellows or greens. So I'd be like, yeah, I would totally go and screw up my sample if I could pick. All red, yeah, all red. That sounds good. I'm down with that. Um, Independent, we need to check 20. N is less than capital N. So I need to check 20 times minus 238. That needs to be less than the number of all Skittles in the world. 20 times 238. I thought I could do it in my head, but I can't. 4760. And that is definitely less than the number of Skittles. I don't know how many Skittles there are, but there's more than that. All right, normal, I need to check N times P times Q. That has to be bigger than 10. So for me, N is 238. P hat is 0.227. I need my Q value minus 0.227 is 0.773. Let's see. 238 times 0.227 times 0.773. I get 41.76. That is indeed bigger than 10. So I get a yes. And as we said earlier, it's okay if you didn't get three yeses. Okay. One of the fun parts of the projects is getting to look at your own data and learn about like how would I do this? Like, what sample size do I need to have, right? So uh, if you get a no here, that just helps you learn next time when we're doing this for real, like if we were doing like an actual medical study, tells you like, okay, I've got experience now in making sure my sample set, because one time I got a no. So, all right, that's all good. Let's move on to number 9. Regardless of whether you got 3 S's, construct a confidence interval for the proportion of Skittles that from your color from number 7. Mine was green using confidence interval, or sorry, confidence level number 2. So now I'm going to be switching to 98.3. That is my confidence level. Yours will be different, right? Yours will be higher, probably lower. Formula, substitution, and result. All right, our formula is still the same. It is it's on page 259. It's p hat plus or minus z alpha over 2 big square root p hat q hat over n. And then for our substitution, so my p hat was 0.227. I'm going to leave space for the z alpha over 2. I'll come back to that. 0.227 is my p hat. Q hat is 0.773, and my n was 238. To get your z alpha over 2, to get your z and to get your result, there's 2 options. One option is you can use a pair of calculators. You can use the StatCrunch normal calculator and the Desmos calculator to get your z and your result. Okay. The other is you can do proportion stats, one sample with summary. Okay. And either one is fine. This time I'm going to do that one first. Okay. And let's walk through that and I'll show you what it looks like. So in StatCrunch, I'm going to close this because I don't want to confuse myself with M&Ms. Stat, proportion stats, one sample with summary. Number of successes, in my case, it was 54. It's your X value. It's how many, I had green, but whatever color you had the most of, you're going to put that number in there. Observations is your sample size. That's your N. We're going to change our blue button to confidence interval. And you're going to put in the confidence level that you got from question number 1. It's the confidence level 2. I had 98.3. Oh, sorry, as a decimal. There we go. And then you're going to check this box right here, show critical value, and that will give you your Z value, okay? So my confidence level number 2 for Skittles, I'm using 98.3. I did 87.3 for M&Ms. I'm switching to this one now for Skittles, okay? And we'll hit compute. And here it is. So I need to write down my Z value, my lower limit, and my upper limit, okay? Let me see if I can zoom this down so I can, yeah, almost. There we go. All right. So my Z value was 2.387. My lower limit is 0.162. And my upper limit is 0.2917. Okay. Your Z value is going to be different from mine. Your confidence interval will be different from mine, but I'm just writing these 3 numbers. Z goes here, lower limit, upper limit. Okay. Now, if you do if you use the calculators, your result might be very slightly different from what you'll get in StatCrunch. The reason for that is rounding, okay? And either of those is fine, okay? You can use either method. I showed you both before. I can show you the calculator here if you want, but for now I'm just going to keep going. Okay. All right. Willy Wonka is bothering you again and claims that the proportion of candies for my color, which mine was green, he claims that uh, green is more than 20%. So I'm okay with the green. I don't like the yellow ones, but if he came to me and he was like, "Hey, did you know that the Skittle company is making more yellows than any other color? They're making more than 20%." I would be up in arms, right? So, um, does my confidence interval support his claim? Well, that depends on whether 20%, by the way, is 1/5. So 1 divided by 5 is 20%. Okay, so that's why he's saying 20%. Um, that depends on whether 20% is in your confidence interval or not. Okay, you don't need to draw a number line. You can just look at it and say, okay, is 0.20 in this range or not? Okay, so for me, 0.162 and 0.2917. I don't know what the true green proportion is, but I know it's somewhere between 16 and 29%. So 0.2 for me is right there. So since mine is in the confidence interval, I'm selecting that one. Okay. For you, if 0.20 is not in your confidence interval, you would be selecting this one. Okay. Did anybody get this one? Uh, did anybody end up with 0.20 being outside? So Rachel did. What confidence interval did you get, Rachel? Do you mind dropping, or Montez, do you mind dropping what numbers you got in here? Confidence interval did you get? So Montez, his confidence interval is between 21% and 29%. Okay. So now we know that, and then Rachel got 20.57 and 28%. Okay. Now we know the actual answer. Normally we don't. We don't know the p-value, right? But here we know that Skittles are made in equal quantities. So 1 divided by 5, 1/5 is 0.20, right? I'm not sure what that is. 1/5, there's 5 colors, is 0.20, 20%. Okay. So why is it that Montez and Rachel got confidence intervals where 20% is not in that range? Well, it's because we have a random sample. So when you have a random sample, there's a chance that the true value is outside your interval. In other words, I am 98.3% sure, I am 98% sure that the proportion of green Skittles is somewhere between 16% and 29%. I don't know what it actually is, but it's somewhere in that range. Now, that means there's a 1.7% chance that I'm wrong. There's a 1.7% chance that the true value of the proportion is outside that range. And that's what's happening with Montez and Rachel. Maybe their confidence is a little lower. Maybe they're looking at like a 70% confidence or a 85% confidence. Okay. When you have a small confidence, so Montez was 75%. When you have a small confidence level, then that means you're going to have a small confidence interval. So Montez is 75% sure. I'm 75% sure that the true answer is somewhere between 21 and 29. Well, that means there's a 25% chance that it's not in that range. And that's exactly what's happening here. 20 there's 25% is not that low. So in this case, what's happening is 20%, the true value is landing in what we call alpha. So Z alpha over 2, alpha is related to your confidence level. Your confidence level, you want your confidence level to be very high. Alpha is called your level of significance. It's your error, okay? It is something you want to be very low. And we put alpha over 2 because you'll remember that in our calculator, we said we wanted to do um, uh, between. So the alpha is the white space. Your confidence level is the red space here. Your alpha is the white space, and it's split in half. Some of the white is over here on the left, some of the white is over here on the right. Okay, and that's why we call it alpha over 2. So anyway, Montez's confidence is 75%. That means his alpha is 25%. Okay. Rachel's is at 92.8. That means there's still like a 7.2% chance. So the white space is 7.2%. So there's a 7.2% chance that uh, your confidence interval is not right. Okay. So how do we fix that? Well, to fix that, the best way to do it is get a larger sample size. A larger sample size means your data is more accurate. Okay, so that's what we're going to talk about right here. Suppose when creating this confidence interval, instead of using confidence, oh, well, no, this is okay. Anyway, suppose instead of using the confidence level 2, use confidence level 1. Confidence interval would have been narrower or wider. For my Skittles, I use 98%. I want to be 98% accurate. If I hadn't used 98, if I'd used 87 instead, if I'd used a lower confidence, then I would have ended up with a narrower confidence interval. Small confidence levels mean small confidence intervals. Large confidence levels means you have a very large confidence interval. Okay, so um, so mine would have been narrower because confidence level and error have a direct relationship. So um, if this number is big and this number is small, they'll circle this one. If it's the other way around, they'll circle this one. If your number 1 was large and your number 2 confidence level was randomly small, you'll want to use this one instead. Okay. Basically, think about it like this. If I want to make, if I'm shooting baskets, okay, shooting baskets with my basketball, okay, and I want to make 98% of my shots. Well, one thing you can do is you could make the hoop bigger. If you have a giant hoop, like a swimming pool sized hoop, you're definitely going to make 98% of your shots. Okay. A large confidence level means you have a large confidence interval. So this true proportion is going to land somewhere in this range. And if I want to be 98% accurate, I need a giant interval. If I have very low confidence, if I only want to make like, 10% of my shots, then you want a teeny tiny little confidence interval, teeny tiny little hoop. Okay. Right. I don't know much about basketball. You can't change the hoop, right? The hoop size. So anyway. All right. We're gonna move on. Um, so we said that some people ended up getting a no when they checked n times p times q. They said, oh, mine's not bigger than 10. That usually means that your sample size is too small. It might mean your p-value is too small, but you can't control the p-value, okay? You can't control what percent of your sample is blue. If you do that, then it's not random, okay? You can't go and just pick out all the blues, okay? So in order to make sure that you're satisfying the requirements, you need to have a large enough sample size. And the larger your sample size, the more accurate your results would be. So let's say we did this and we found out, okay, we got a no here. Or let's say we did this and our confidence interval is too big. I had a confidence interval that went from 0.16 up to 0.29. It was a massive confidence interval. That's just too large. Okay. So if you find yourself in that situation, then you say, okay, we need to redo this. And this time, let's use a bigger sample size. Well, how big of a sample size do you need? That's what we're going to calculate for number 12. So page 573, number 12, calculate the minimum bag size, as in how many candies do you need, to ensure that the proportion of your M&Ms is within 2% of the true population proportion for that color. Use confidence interval number 3, and assume you do not have a prior estimate. What the heck does all that mean? Well, okay, so we need our formula. We need a substitution. And we need a result. Okay. So within 2% of the true population proportion means I want to be much closer. I want my sample, I know that my sample is not going to be perfect because it's random. Okay. But it's going to be close to the true value. How close? Well, I want it to be this close. I want to be within 2%. I was not within 2% on this last one. Um, my margin of error, I was looking at between 16 and 29. That's a range of 13%. So that means my error was half of that. My error was 7%. That's a pretty huge error. I actually want a much smaller range. I want my confidence interval to only be like plus or minus 2%. Okay. So that's my error. Okay. And I'm going to use confidence level number 3. We said that confidence level 1 was for M&Ms, 2 is for Skittles. This one is going to be for calculating sample sizes. So now I'm going to be using this confidence. And the formula that I need is on page 261. Okay. Page 261, single population sample size formulas. In other words, how many how many do I need in my sample in order to be, you know, as accurate as I want. Okay. This is for proportion. There's also a formula down here for means. We're going to use the proportions. Okay. And there's two of them. One is if I have a prior estimate, and one is if I don't have a prior estimate. And we're going to use both in a second here, but we're going to start with assuming I do not have a prior estimate. So I want to use this one here. This is my formula for a sample size. So n equals 0.25 alpha over 2 error rate squared. All right. So my previous sample size for M&Ms was 140. And let's say we decide, yeah, that's too small. I need a bigger sample size. How big? Let's figure it out. My error is 0.02. I want to be within 2% of the true population. Write that as a decimal. So there's that. Z alpha over 2, that's going to be different for everybody depending on what level you're looking at. So I'm looking at 94.8. So let's go to StatCrunch. And you're going to do stat calculators normal. Stat calculators normal. We're going to switch to between. Confidence intervals are always between. And you're going to put in your confidence level that you want. I want 94.8. And my Z alpha over 2 is 1.9431. Okay. So I'm using this confidence level. I put it into my calculator. Stat calculator is normal. Put that in right here for my between. Hit my compute, and this is my Z value. All right. And then my result, this one I'll do in the calculator. So we're going to type that in. Let's see what we get. 0.25 times big old parenthesis 1.9431 divided by 0.02. Close your parenthesis. To do a square, you do Shift 6, which is the little up caret arrow, and then you hit 2 to square that, and I get 2359.77. Now that is not the answer, okay? Because I can't get a sample size of 2,359.7 M&Ms, okay? What does that mean? I take a small bite of one and leave and use the rest? No. You want this to be a whole number. Sample sizes are always whole numbers. But when you round this, you always need to round up. Okay? So my sample size is 2,350. Sorry, I have to round that up. 60 M&Ms. Okay? If this had been 2359.10, I would still round it up, okay, to the next whole number, okay? And the reason why is because if you round it down, then what that does is it means your margin of error is not going to be 2%, it's going to be like 2.1%. And I don't want that. I want to be within 2%. So rounding up means it'll actually mean my margin of error is like 1.9%. I'm okay with that. Okay, I want to be within 2%, and 1.9 is within 2. So that's fine. Suppose when completing number 14, you would use a 1% margin of error instead of 2. So if instead of putting 0.02, I would put 0.01. Your sample size would have been smaller, larger, or the same. What do you guys think? Larger, smaller, or the same? What do you guys think? Give me a guess. It's not a test day. You just guess. You got a 1 out of 3 shot of getting it right on a guess. So an error of 1% is more accurate than an error of 2%, right? The smaller your error, the better. We want our error to be small. So a small error rate, so more accurate, means a larger sample size. Let's actually check that. You don't need to check that, but I'm curious now. If I had put in 0.02 and I instead put in 0.01, my sample size is now 9,000 M&Ms. That is a huge jump. It went from 2,000, which is still pretty big. It jumped quite a lot. So more accurate means a larger sample size. Okay. All right. Next, calculate the minimum bag size again with the same confidence and same error as a number 14, but this time use a prior estimate. So we said we do not have a prior estimate. That's actually wrong. We do have a prior estimate. We did a sample size of 140 M&Ms or however many was in your bag, and I got a p hat, and we said, oh, well, that gives us a margin of error that's too wide, or there's a problem with it, like maybe this is a no. We need to redo this and get a new sample. Well, I already have a prior estimate. So I shouldn't have used that formula. I should have used this formula. This formula is what you use if you have a previous p hat, which in this case I did. So let's use that one instead. So our formula and our substitution, and a result. Okay. Formula is n equals p hat q hat z alpha over 2 error squared. Substitute in my n for M&Ms was 0.150, which means my Q hat was 0.850. Your Z alpha over 2 is still the same as what you calculated up here. So I'm still using that. So I'm just going to copy that here. And I'm still looking at a 2% margin of error. So same confidence, same error. So 0.02, square that. So really all I'm changing is the 0.25 out here is now p hat q hat, right? I'm going to retype this guy. 0.150 times 0, times big old square, or big old parenthesis, 1.9431. That's my z value. You're going to have a different one. And you also have but you're going to have the same 2 there. Shift 6, 2 to square that. So now my n is 1,203.4. Okay. But that's not my answer. I need to round that up. So normally I'd round that down and say 1,203. That was not the right direction. I want 1,204 M&Ms. Okay. So if I was going to do this experiment again, I'd want to make sure I'm getting this many M&Ms. Okay, so that's quite a lot more. Gonna need some friends to help me eat that when I'm done. Of the 3 confidence levels, which would yield the largest sample size? So uh, these are the confidence levels that I had. And we said that a larger sample size means more accurate. So in my case, the most accurate one is this one. 98 is my biggest one. So that is going to be my largest sample, is going to be my largest sample size. So you're going to look at which confidence levels you have, which one is the biggest. That's the one you're going to circle here. Okay? Because confidence is how accurate you are, right? And a larger sample size means more accuracy. Okay? All right. So make sure you upload this for the Chapter 9 project in the Canvas. Make sure you do your lecture notes. And if anyone has questions, I can stick around. Otherwise, I hope you have a good